Good morning, everyone. My name is Radkevich, and I will be talking about radiative transfer theory and its application for retrievals of bidirectional reflectance distribution function from surface reflected radiance. So I'd like to start from basic equations and definitions. Bidirectional reflectance distribution function is defined as ratio of surface reflected radiance and downwelling radiance at surface level, provided that all downwelling flux comes from single direction. BRDF is required to set up boundary conditions for radiative transfer modeling, which is used in aerosol retrievals, cloud retrievals, computations of Earth's radiative budget. So radiance of light can be presented as a sum of direct unscattered part and diffuse part. And diffuse part is governed with radiative transfer equation, which is in one-dimensional case has form of equation 1. And 1D case, I mean that nothing depends on horizontal position. All properties of all functions depend only on vertical position. Since this is an integral differential equation, it has to be supplemented with boundary conditions. And I will consider three different boundary value problems. First problem is schematically depicted in the left figure. Atmosphere is eliminated from its top, and at the bottom we have reflecting surface, which is described with BRDF III. In this case, boundary conditions are given with equations 2. The second problem is similar, but there is no reflection at the bottom. In this case, boundary conditions are given with equations 3. And the last problem is, say, same atmosphere, but flipped over. Atmospheric layers are just taken in inverse order. In this case, boundary conditions has form of equations 4. I will denote the solutions of these three problems with letters L, I, and J. And some time ago, I found a relationship between these three solutions and BRDF III. It is given with the equation 5. I'm sorry, it is hardly readable, especially taking into account that the last term on the right is quadruple integral. But it can be simplified in the form of 6. So this is an integral equation, Fredholm integral equation of the second kind, where the source function S and kernel are given with expression 7. Usually what people measure is radiance L at optical thickness of tau t. We can't measure surface BRDF, which is property of surface itself. We only can measure reflected radiance. And the problem is how to derive BRDF, again, as a property of the surface from the measurement of reflected radiance. Equation 5 can be inverted, well, basically rewritten in the form of 8, where the source and kernel of that equation are given with equations 9. The problem is that likely this equation is ill-posed problem because the exponential factors in both S and K can get really huge. And we'll see that this causes a problem with solving equation 8. But if we look at these two equations, 6 and 8, we can see that they have similar form. So it makes sense to consider an equation of that form and try to solve it and at least develop methods of solving it. So let's say consider equation 10. There are several approaches to solve it numerically. Say textbooks offer successive approximation approach, which says take source function as an initial guess and then substitute it into the equation and iterate it as many times as necessary. However, this method may not converge in quite simple cases. I just wrote one of them. It's funny, but it's true. The equation can also be solved with quadrature method. But if we discretize the equation for the function of two variables, we can end up with a linear system of linear algebraic equation of great dimension. And so we need to develop effective methods of solving it. So discretization I use is based on Gaussian quadrature with respect to polar variable mu and regular grid with respect to azimuth angle phi. So when I apply this discretization, I end up with the system 12, where source vector, which is actually a matrix, f, j, i, and matrix of the system itself, k, are given with expressions 13. It seems that direct solution of this system, well, may take a lot of time because of the dimension of the system. So from my point of view, iterative methods can be more efficient in this case. The next slide summarizes stationary iterative approaches for linear systems. Richardson iterations is basically a discretized version of successive approximations for integral equations. And this method is the least efficient. Theoretically, Gauss-Seidel iterations is the most efficient method, but sometimes in order to get control on how far the next iterate jumps from the current iterate, it may be useful to use relaxation. So successive or relaxation method just blends current and next iterations obtained with Gauss-Seidel. So I will consider this method in the case of two-dimensional system of linear equations. And here is mathematical implementation of that. Well, code is trivial, probably, but basically I use Mathematica in order to verify my Fortran codes. So I don't basically use fancy features Mathematica provides. I need just simple instrument that can get a result quickly. Let me go back a little bit. I need to initialize the system to show how it works. Oops. Yeah, okay. So I will need some other routines, auxiliary routines to perform actual computations here. They are basically integration routines, quadrature computations, and file reading and printing. So here we go. The first case, pristine atmosphere, no aerosol, surface, bottom surface is described with BRDF given by Nielsen-Kusk, equation 18. In the atmosphere, we have only Rayleigh scattering, so scattering phase function is fairly simple. Optical thickness of the atmosphere I chose of 0.1, which roughly is about green light, 550 nanometers. So discretization scheme is described here. The code presents just general setup for calculation. Here I compute kernel and then kernel matrix. And here is the iterative process itself. You see, at the very beginning, it does not converge, but beginning from iteration number 8 or 9, it starts to converge for everything. And finally, the process converges using probably 22, 23, 24 iterations. In this computation, I chose relaxation parameter of 0.9 given in magenta. Empirically, I found that this value provides the fastest convergence. Unfortunately, this method may not converge at all for more complex problems. I will talk about that later. But now I just want to show how accurate the solution is. On the right is the solution I just obtained. In the middle, result of radiative transfer modeling with code dissort. And relative difference, sorry, in the middle, dissort modeling, and on the right, relative difference between them. We can see that relative difference is small for almost all solar zenith angles except this one, the very low sun. In this case, we see relative difference huge. Well, we can say two solutions are of the same order of magnitude, but it's actually bad. But in the remote sensing community, nobody cares about so low sun. So that's OK. From the perspective of remote sensing community, that's completely OK. Accuracy is great. Now let's consider a little bit more complicated problem. I add some aerosol load to the same atmosphere. So I considered transported mineral dust aerosol model with optical thickness of 0.1. So total optical thickness of the atmosphere is 0.2 now. And I used the same BRDF model, but slightly less reflective. Parameter A, which defines how bright the surface is 0.2 now instead of 0.49. And I will not perform any computations here now. I just want to show that exponential factor I talked about is really, really huge. And unfortunately, iterative process does not converge with any relaxation parameter. I tried many of them. So, however, it makes sense to solve direct problem rather than inverse problem. So solve for reflected radiance rather than BRDF. And this slide presents the code setting up computations. And these slides present computations for 3 different relaxation parameters. I begin with parameter of 0.9. And we can see that iterations converge quickly. So for any solar zenith angle, no problem anywhere, really. But what if we do not want any relaxation? So if relaxation parameter is 1, so just Gauss-Seidel iterations, we can see that the same iterations converge even faster. We need only 4 instead of 7 before. Well, we can expect that if we increase relaxation parameter even more, we can get even faster convergence. But unfortunately, that's not true. With 1.1, we have, again, 7 iterations. So it seems that for direct problem, we do not need relaxations at all. So here is the comparison between the result I just obtained with Desort modeling and relative difference between them. So the difference is fairly small, but starting from a certain solar zenith angle, we can see noisy behavior of the Desort modeling. Brief explanation of that is that it is obtained with summation of cosine Fourier series, and it is done with single precision because of the design of that code. So probably the method I developed can get better quality of the solution. Now, it is important to see the contributions of different terms of the equation I considered to the total solution. So I considered the direct light contribution given by equation 20, and my initial guess given by the sum of first 2 terms on the right-hand side, and the total solution. So the comparison is shown in this animation. Direct light contribution on the right, initial guess in the middle, and the total solution on the right. So direct light contribution is significantly smaller than total solution, but initial guess provides almost full solution already. So this gives a hint how to solve inverse problem using the direct problem solution. All we need to do is to assume that BRDF can be presented as a sum of linear combination of unknown functions, and the problem reduces to the search for the coefficients of this linear form. In this case, source function and kernel function are presented as sums of known functions again. And the iterative approach for this problem is 2-stage. At any iterative step, we have to perform 2 operations. First, we need to find minimal square feet of reflected radiance. As at the initial guess, we use only source functions. And then we find coefficients alpha naught and use them to compute approximate reflected radiance at all directions necessary to evaluate integral that defines model functions of the next step. The next step, we feed model functions, different model functions from the first step, and find coefficients of the linear form for that step, then use them again to compute next approximation of reflected radiance. and so on and so on. So we need to solve one more problem. Model functions are not known in their functional form. They are given as tables at certain values of their arguments. So custom function linear fit solve the problem of this fitting. It's nearly trivial. And again, I will consider the case I used with direct problem. Kernel functions for BRDF are just the same function used in actual BRDF, but I assume that now I don't know the coefficients. So this code basically sets up everything, chose random directions, and thus pretend to simulate actual measurements. So these random directions are then used to retrieve values of reflected radiance from my modeling results I used before. And this code here is just implementation of the iteration process I just described. So here how it works. Surprising thing is that we do not need actually many iterations, because after iteration number 1, we don't see any change with 6 digits. They are all the same. Each iteration, unfortunately, takes quite a long time, well, at least with Mathematica implementation. But the matter of fact is that we need only one of them. We don't need to perform 5, 3, or whatever. Just one of them is enough. So this slide shows another example. I chose randomly again certain directions, 15 directions. Positive part of x-axis shows solar zenith angles, and scattered dots show random directions of observations. And in this case, here is the comparison of the my solution and theoretical values used to obtain, say, reflected radiance with radiative transfer modeling. We can see that in the worst case of coefficient alpha 4, relative error is about 1.5%. I'm really not surprised to see that, because we saw that the difference between the sort solution for reflected radiance and my solution can be about 2% easily, and the sort solution I use as a model measurement is quite noisy. So I consider this result is, well, as a success, really. So here is my conclusions. A method to solve a Fredholm integral equation of the second kind of 2 variables was proposed. The method was used to solve the equation relating surface reflected radiance and BRDF. Solving for BRDF is ill-posed problem, and iterations may not converge, while direct problem for surface radiance is well posed, and iterations converge very quickly. So this gives an idea how to develop iterative procedure to get BRDF, assuming that it is presented as a sum of known functions. And this iterative process converges really quickly. That's all. Thank you.